I would like to welcome our guest, Professor Adri van Duin, and Professor Feliciano Giustino, who is going to join us at 11 o'clock Eastern Standard Time. So this is the Carbon MEMS, what we call AxelNet, a network of networks, summer school for 2025. So we've done this last year. This year's theme is simulation and modeling in the discovery of new hybrid materials and carbon, or even understanding the carbonization of some of the polymers that we use. So we thought we should focus completely on simulation. So over the next 3 days, you're going to see talks given around this. So let me introduce our guest, Professor Duin. So Professor Duin is an inventor and main developer of the Reactive reactive force field method, which a number of you are using already or are considering using. This software enables large-scale, greater than 1,000 atoms, fully dynamically, fully reactive simulations on complex material molecules and their interfaces. Professor Duin is a distinguished university professor of mechanical engineering, chemical engineering, engineering science and mechanics, chemistry, material science and engineering, and director of the Material Computation Center. His research interests include atomistic-scale simulation of chemical reactions, reactive force fields, quantum chemistry, combustion reactions, and interface chemistry and organic chemistry. Professor Duin, the stage is yours, sir.
Thank you very much for the kind introduction. And once again, thank you very much for setting up this workshop and inviting me to present. Let me go and share my screen. And go into presentation mode. I should hopefully be visible on your end right now.
Yes.
Great, thank you so much. All right. Oh, what happened there? There we go. All right, so yes, as mentioned, so I will talk about the reactive force field methods, which indeed allows us to perform relatively large-scale simulations, 10,000 atoms and beyond, and that allows us to go to complex materials, or materials that are sensitive, so I'll present primarily applications to 2D materials with a focus on carbon-based materials, but every now and then you'll see me mention other 2D materials, but don't worry, I'll get back to graphitic materials eventually. What I'll be presenting has a strong contribution, particularly for Margaret Kowalik. Margaret Kowalik is a research professor in my group, and she's been pretty much leading the carbon-based applications in my group. Chan Mao and Nadir Nair are also research professors. Nadir actually moved to PDI Berlin last year. Let me show you that this is my current research group. So I have 4 research professors affiliated with my group. I already mentioned Margaret or Malgorzata Kowalik. And so as you see throughout there, there's a very strong interest in 2D based materials. Also recently, we have had various projects on silicon carbides, which clearly by themselves also have an innate relationship with graphitic materials. And so that will come back in my talk every now and then. I'm also serve as the director of the Material Computation Center at Penn State. So this tries to kind of incorporate theory into material synthesis. And what we really would like to do right now, most of the time we spend in explaining experimental successes or failures as such, but preferably successes, of course. But we really would like over time to really turn the table around, that we actually predict for the experimentalists what are the kind of the good synthesis windows to look at. And so we are beginning to make some progress on that, and I'll see some examples of what we do there. And the reason for this is that compared to experiments, these atomistic simulations are relatively inexpensive. They're not for free because compute time costs time, and even theory people have to eat. But it is really still pretty inexpensive, and we can then try out things that experimentalists are not ready to do yet. So we can say, okay, now this synthesis worked great, but now let's reach across the periodic table and add a new element into your synthesis window. Let's see what it does. Now, that's not something that for an experimentalist can take various months to do. They have to quite often completely rebuild the experimental setup. For a theory person, it's just as simple as kind of, clicking a button, getting a new element in there, make sure clearly that your theory tools are appropriate, and you can check out if it works. And that's the type of feedback loop that can be incredibly helpful for experimentalists. So when they actually make that effort, that they have a reasonably good chance of success. Also, for the last over 10 years now. So we've been trying to take our work to some extent in a commercial space. I started with my wife a consulting company called RxWF Consulting. That was based so Reactive is now incorporated in various environments, including LAMPS, the AMS, which is released by SEM Amsterdam. And so that has included, that has started a pretty large interest also from the industry side. But industry quite often wants to have sort of proprietary force fields, so force fields that don't make it in the open literature. And so in my company, we can indeed develop these type of parameters for industry, but also sometimes indeed for academia. So that that works pretty well. These are people that have molecular dynamics capabilities, but they don't have force field development capabilities. And so my company can cater to these type of needs. All right, let's see where we are now. So this is a typical a picture of multi-scale simulation. So at the bottom left, we have quantum mechanics, highly accurate, arguably the most accurate method that we have to calculate chemical interactions. They're not perfect, but they're pretty impressive. And clearly, there's clearly a lot of methods within quantum mechanics. The bottom line is here for this presentation is they're fundamental, so we don't have to take any major approximations, which is helpful, and no assumptions, but they're computationally very expensive, and so typically they're only used for relatively small systems. And now what small means, let's say, 500 atoms is still pretty big for quantum mechanical simulations. Also, a time scale perspective, people are doing ab initio-based molecular dynamics, but that typically is in the realm of picoseconds. It's very hard with ab initio-based molecular dynamics to go to a nanosecond or even a microsecond scale. So that's why force field methods exist. Sorry, was there a comment? Okay, that's why the force field methods exist. They are empirical. So now we stop trying to solve Schrödinger equations. We just pick a set of physically reasonable equations, but they are empirical. So the parameters need to be trained. So we lose that fundamental concept, but they're computationally much cheaper than quantum mechanics, millions of times cheaper. And so you can easily apply them to much larger systems. And size is important because if you stay with small sizes, you are stuck into high symmetry materials. You cannot really study defects and interfaces very easily. So there clearly is a need to do large scale simulations in that realm. Okay, so if we then look at, if we want to do reactive molecular dynamics, so we want to change conductivity during the simulations, once again, we can stay within quantum mechanics, so we can do ab initio-based molecular dynamics. And that's going to be expensive, but it certainly is a viable option these days, and there's many examples of people performing that, but it's still pretty small and pretty short distance. You can then also make quantum mechanics faster, so you can go into the realm of semi-empirical methods, and especially tight binding DFT has been very popular in that area. So that provides you a much faster, still ab initio, or at least still kind of wave function based approach. And then option 3, that's the approach that my group has been using, trying to make force field methods more sophisticated and allow them to break and make bonds. And this field was really initiated in the late 1990s by Tursoff and Brenner, who made the first force fields that actually could make and break bonds during simulation. Also, the embedded atom potentials are very popular in that particular domain. So these are very often called sort of the first generation reactive force fields. Reactive is part of the so-called second generation reactive force fields. So a similar generation with the cone potentials and the MEM potentials, which typically contain, for example, both weak interactions and strong interactions. So the Tursoff and Brenner potential typically only describe the strong interactions. They don't do very much for the van der Waals and Coulomb interactions. The second generation force fields also contain van der Waals and Coulomb interactions. Now, what Reactive is really very much focusing on, and I'll show that in the next couple of slides, is trying to get transition states in the right area. So trying to get the energy of transition states right. That's the one thing that really has distinguished Reactive from many of the other methods mentioned here. Now, over the last couple of years, we have an option 4. We have also now neural network-based potentials, which are very, very capable. And they have very, very good capabilities. They have also very interesting weaknesses. And so we have to kind of see, I'll be happy to discuss this with people here. And I've very extensive communications with neural network-based groups. We actually published some joint papers together recently. And so the communication between physics-based methods like Reactive and neural network-based methods is certainly something that over the coming years we'll see how that connection works out. Okay, so my tool of use is Reactive. Reactive F is a bond order-based potential. So the central equation in Reactive F, by no means the only equation, is the equation that I have here in the center, where we relate the interatomic distance Rij to a bond order. So bond orders are a well-known phenomenon. It was introduced a long time ago to describe metal and metal oxide systems. What we do, so we know, for example, about single, double, and triple bonds in carbon-based materials. What we do in Reactive F, we assume that the bond order can take any positive number. So it can be a value of 3, 2, and 1, but it can also be 2.5 or 0.2. So it essentially is a continuous number rather than an integer number. And with that concept, we can essentially pretty much plug in the interatomic distances into this equation. A bond order comes out, we can calculate associated forces, and we can do molecular dynamics where we break and make bonds during the simulation. Now we know clearly from non-reactive organic force field that angles and dihedral interactions are very important to consider. So we include those in Reactive F as well, but we make them bond order dependent. So we multiply an angle term by a bond order term. So if the bond order goes to 0, the angle term automatically goes to 0 as well. Then Reactive F, as I mentioned in the previous slide, is a second generation force field, reactive force field. So it has a full suite of non-bonded interactions, in particular van der Waals and Coulomb interactions. What is unique to Reactive F is that they are calculated between every atom pair. So we don't do exclusions. Every atom, even atoms that are sharing a bond, get a van der Waals and Coulomb interaction. Now, for the van der Waals, that's not that important. It doesn't make that much of a difference, but Coulomb interaction is actually pretty relevant. So Reactive F, because it calculates an on-bond Coulomb interaction, can make a transition between a covalent material where there's not much charges on a bond and ionic material where there's actually a lot of polarization on a bond. So for a highly polarized bond, the Coulomb interaction provides most of the bond strength, while, for example, for a covalent bond, like a bond between nitrogens in N2, for example, that is almost exclusively a bond order based. So you can actually switch between ionic materials and covalent materials. And so every iteration we update charges. We use the EEM method by Mortier and co-workers, very similar to the QEQ method. So that means every iteration, so that means, for example, if you have an oxygen molecule reacting with a metal, when the oxygen molecule is far away from the metal, it's roughly neutral. The metal surface is roughly neutral. When it approaches the metal surface, it begins to transfer charge. And in the end, we get a negatively charged oxygen atom, O2 molecule that dissociates into negatively charged oxygen atoms. And that's kind of all this charge transfer is calculated continuously. So here's roughly how Reactive F works internally. We start with the atom positions. We switch them between non-bonded and covalent interactions. So we calculate bond orders. We do a correction and then we find angles and torsions. And then eventually we calculate all the bond angle and torsion contributions. Similarly, completely independently, we calculate charges. We calculate van der Waals interactions and Coulomb interactions. Oops, there's something in the chat. So we separate the system charges into various independent charge contributions. And so the reason why we do this, Reactive F is not more accurate than DFT. It can approach density functional theory accuracy reasonably well, but it's always going to be less transferable, but it is much, much faster. And also Reactive F is much faster than most neural network-based potentials, with some exclusions here and there, but so it's roughly about 1 million times faster than DFT, but the bigger the system gets, the better that comparison becomes, because Reactive F scales roughly linear with size, while DFT scales typically with n to the power 3. So if you double the amount of atoms, DFT becomes 8 times more expensive. Reactive F just becomes about 2 times more expensive. Reactive F is also fully parallelized, so there's a parallel version available within AMS and within LAMPS. So you can essentially run systems on pretty large systems, run MD simulation on pretty large systems, easily 1,000 atoms and beyond. So the speciality of Reactive F is, and that's really where we're focusing on quite often in development, is doing barriers and intermediates. So we really try to get reaction coordinates reproduced from DFT. Here's an example of, for example, a methanol reaction to carbon monoxide on a platinum surface. So you see here the red bars here are from quantum mechanics, and the Reactive F kind of wriggly lines because this was done with a low temperature MD simulation, so there's a little bit of temperature noise. you see that the reactive F trajectory follows the DFT trajectory quite well. We get the transition states in the right place, in the right height, and we see all the intermediates show up in the right place. Also, we can look at competing reactions. So a very important competing reaction for methanol dissociation of platinum. Here's the gray curve, they are there. The breaking the CO bond is very, very high energy on platinum. And so indeed on platinum, we know that platinum gets in fuel cells, suffers from carbon monoxide poisoning, because there's really no way out. You really all the way go down to harvesting all the hydrogens, you end up with carbon monoxide, and carbon monoxide pretty much occupies your surface. So, but the important thing is our main target in training is really trying to get those transition states in the right place. And for that, we sacrifice sometimes, quality of geometry and all that. But the transition states are very, very, very strongly focused on. So we started with hydrocarbons in 2001. And over the years, we managed to take the method across the periodic table. So many, many elements are now available in Reactive F. The ones that are not available is simply because we haven't had projects for them. Actually, sorry, this picture is not completely up to date. We now actually recently developed a scandium force field. We also have a tin force field, which I'll talk later about. But any missing elements, we can certainly develop potentials for. Now, this picture promises a bit more than we have because it doesn't tell which elements can interact with each other. So we have, for example, a titanium oxide force field, but we don't at this moment have a titanium fluoride force field. But all the things that we don't have, we know how to develop. Nice thing is that all these force fields, all these react force fields use the same functional form. So they can very easily be combined. And so you can essentially use them pretty easily for interfaces and all that. We have distributed the code to many, many different research groups. I'm not in charge of the LEMS distribution, so I have really no idea how many people use the LEMS reactor, but it must be many, many thousands of people. I personally have distributed over the years the code to probably about 3,000 or 4,000 people. My group primarily now uses ADF or AMS Reactive F because it's a little bit more efficient than LEMS for small scale simulations. And it is also pretty user friendly. It has a very nice graphical user interface. So that's the main code that my group uses, apart from my standalone React development code. Very quickly going over some examples before I go to the more graphic thing, just to show you the diversity of research that has been done with Reactive F. So a big increase in popularity was in 2008 when we developed the first combustion react description, where we actually could simulate pyrolysis and oxidation. And then we managed to transfer that into catalysis. So we could look at, for example, how the carbons interact with chromia and other types of catalysts. Similarly, we have done much water-based research. I won't talk too much about it in today, but you can do things like water dissociation on oxide surfaces. And if you large-scale simulation, you can, for example, do these type of simulation where you have small oxide particles. You can simulate their clustering and how water affects their clustering. We've done much work on hydrolysis reaction on mineral surface. Hydrolysis is a very important reaction. It is very environmental dependent. It depends on the strain, the type of materials, and all these type of things. And we can take that to larger scale, where we look at, for example, at chemical diffusion. And so we can look at water dissociation and diffusion in very complex interfaces. One of the earlier applications of Reactive F was high energy materials, so pretty much explosives, where we can simulate the chemistry, the physics of these materials, and we can do, this was work from the University of Southern California group, from Priya Vasista and co-workers, where they can, for example, look how shocks on high energy materials can transfer into chemistry. We have done much work on batteries. For example, here's some examples of how we train a lithium sulfur force field. We can look how lithium interacts with complex carbon materials. And this allows us for the first time, this was done roughly now 10 years ago, we actually can look at a real carbon anode with all the complexity. A carbon anode is not just a couple of simple graphitic sheets. It's a much more complex type of environment, like for example, these type of carbon onions are very popular. And we can look at how lithium interacts and how lithium actually reacts and changes the carbon network during charge-discharge cycles. A more recent focus in my group has been 2D materials, especially chalcogenides, so molybdenum disulfides, very much structurally similar to graphite. We also worked extensively on MXenes, so these are, in this case, these are titanium carbides, but it can work with many different transition metals. So we had collaboration with Yuri Gogotzi's group at Drexel, where we developed many different MXene potentials. And then we did things like extreme chemistry of graphitic materials. This is, for example, a nice simulation that shows the React's capability. This is a collision of silica. We're traveling at 5 kilometers a second, so the type of speeds that you might find in space environments, and hitting a graphitic material where we see a big sort of shock expansion combining with the chemical damage of the silica. So we can actually simulate both the physics of the collision and the chemical response. So here are just some quick examples. Let me now show some more details and carbon-related details. So this is typically how a React project goes. We first train a force field against quantum mechanical data. Our training sets are typically a bit smaller than the data sets used by neural networks. So typically we use something like several thousand data points rather than the millions of data points. But we very strongly focus particular chemical events, like for example here, oxygen binding at various sites of silicon carbide, oxygen migration, and transition states. Then we start small-scale simulations. These are typically single-process simulations, smaller than 4,000 atoms, just to make sure that the force field shows the right behavior. So here we start with silicon carbide, we expose it to oxygen, and we see indeed that its phase segregates into silicon oxide and graphite, so that looks good. That indeed confers, is in agreement with experimental observations. And then we can scale things up. This is once again the simulation from the University of Southern California group, who very much had spearheaded very large-scale MD simulations. So this is roughly 4 million atoms, where we have a spherical silicon carbide exposed to an oxidant, in this case oxygen. And we see during after about 1.7 nanoseconds, this is actually a cross-cut through the silicon carbide particle. We see this beautiful graphitic type sort of material emerging, surrounded by an amorphous silica that kind of protects the graphitic material from further oxidation. And so this is indeed a popular application in space environments, where during re-entry you can essentially shield your polymer-based material from oxidation by embedding some silica-based material in there. The silica makes a nice sort of high temperature resistant and chemically resistant glass that shields the polymer or the graphitic material from further chemical damage. So we've looked extensively at carbon-based materials. So this is a slide from Margaret Kowalik showing the type of structural changes we want to look at. For example, how we want to grow carbon black, so soot-based material, but also how we can turn polymers and carbonize them and turn them pretty much into carbon fibers. So these are both areas that our group has worked extensively on over the last 10 years. Here's some example of the type of simulation we can fairly easily do. That is polyacryl nitrile, a very popular carbon fiber precursor. So this is essentially the structure. It has this sort of very nice ladder structure where we have nitrogen atoms on the top and carbon at the bottom. Now, this structure by itself actually is very hard to carbonize. To carbonize it, you typically first have to oxidize it. And then the oxidized system, you can essentially take to high temperature and carbonize it. So now, naively, you would say that, well, this looks essentially already like a carbon fiber. So if you graphitize it, you think, okay, we just remove those nitrogen atoms at the top, replace them with carbon, and we're done. It turned out that the project, that when we actually do React simulations, it is not as simple as that. We actually see indeed that there's chain dehydrogenation, so we lose some hydrogens and we do indeed see carbonization, but there's also extensive communication between the chains, and so we see carbon growth in the direction of the chain, but we also see graphitic growth between the chains, so it is much less predictable as we thought initially. And so here you can see a sort of a snapshot from a simulation. So you see, look at the black atoms. These are eventually going to grow into a larger graphitic area. So we have the rest of the environment is kind of faded out a little bit, so you can focus on actually the growth. Every now and then you see a new carbon atom getting added to the material, and eventually they'll start to grow a more interconnected graphitic material. But as you see at this temperature, so this is roughly 2500 Kelvin or so, these materials, this is not a clean process. There's a forward pattern. You see that there's clearly the molecular mass is growing. We see some early 5-membered rings getting growing. The 5-membered rings are typically kinetically more stable, but eventually when we get better conductivity, they turn into 6-membered rings. But it's not a straightforward process. By no means a sort of a very clean defined process. There's all sort of stochastic processes going on. And indeed, after We can, for example, now see how a random structure from a line structure changes. In our React simulation, we can also see how oxidation changes these kinetics. And we can follow, as a function of time, the type of rings that we form. And we see indeed that we form a backbone of 6-membered ring, the green curves over here. But at the edges, we see many defects show up, especially 5-7 defects and other types of heteroatoms, where we have heteroatoms where there's still some nitrogen remaining in there. So the process is rather complicated. And interestingly enough, you can actually direct this process. One interesting thing that you can discover is that how additives change this process. And a very popular additive that we tried out was essentially using carbon nanotubes as additives. And we found indeed that the carbon nanotubes can kind of direct the growth. So without the carbon nanotubes, you get kind of growth in all sorts of directions. It's very hard to control it. With the carbon nanotubes in place, we actually can control the growth, and most of the new growth actually happens parallel to the carbon nanotube growth. So this was published in 2023. And we can essentially then, our analysis shows that indeed the presence of the carbon nanotubes adds a local strain in the material. And even though that strain may not look like much, that strain is enough to kind of help the deposition of new carbon material. So we can indeed see that here you see our carbon nanotubes. You kind of see the carbon nanotube wall, and you see how indeed the new growth now happens very much strongly parallel to those carbon nanotube chains. So these tools are very useful to actually check how we can control the carbon fiber growth and what type of additives are going to be efficient in there. And also importantly, how good quality they need to be. I mean, clearly carbon nanotubes can be very expensive, but if the size and the chirality of the carbon nanotube doesn't matter that much, then these materials can get much cheaper and become actually a much more credible additives. So we can see how the quality of the carbon nanotube can affect essentially the graphitic growth. So recently we started looking also at how temperature can affect it. So there's different modes of temperature. Yeah, we can have relatively slow temperature, so sort of a long-term furnace where we very steadily heat up the material. We can do a sort of a short-term furnace where we have a more rapid ramp. But also what's very interesting is how this type of furnace-based growth changes from laser-based growth. So in laser growth, we provide kind of a sharp pulse. And we can clearly do the sharp pulse at various levels. We can have a sort of a lower very energy pulse, we can have a higher energy pulse. It turned out that these pulses very strongly affect the way that the carbon grows. So this is actually a relatively new collaboration of the last 2 years with Randy van der Waals at Penn State. Randy's group has put this really fascinating microscopy together, where they first grow benzene-based soot, and it very much looks like any soot you'd see. It's very hard to distinguish the benzene-based soot, for example, from a ethanol-based soot. But when you expose it to a laser, the soot structure turns very significantly, and then suddenly the material it was grown from, either benzene or ethanol, starts to matter. So the signature of where the material was grown from really comes out when you expose these to lasers. And so in our simulation, we can play all these type of games. We use the same material. We use here C32 as a growth, so a larger scale polyaromatic hydrocarbon. And we can expose them to high intensity lasers, low intensity lasers, short-term furnace and longer-term furnace. And you can very clearly see how that affects the carbon structure. So we're now also using all sorts of machine learning tools to really kind of distinguish the morphology. But you can see that we get a much more open lamella type sort of structure compared to a much higher density kind of compact graphitic structure. So this is kind of new for our group. We also now starting to look at how, for example, oxygen, if you have a low level of oxygen, how that affects these type of things. So you can really look at signatures of the carbon growth. Changing to a new material for a second. So boron nitride is clearly very isomorphous to graphitic materials. So we have been looking at how to grow these with Reactive. We have a kind of a self-training process going on. We first train the force field against a couple of sensible reactions. Then we do some high temperature simulations with that force field. We generate a large amount of low molecular weight species. We go back to DFT, and you see initially this force field actually is pretty bad. There's really a very bad fit between Reactive and DFT. But we add these things to the training set. In a couple of cycles, we kind of get a force field that actually becomes predictive and actually becomes much more accurate for these systems. And then we can look at what sort of precursors to use. For example, a big question in the experimental literature is, are we going to use an HBNH precursor or a BN precursor? It turns out that an HBNH precursor grows much slower, but you get much better sort of 2D type sort of materials, while the BN precursor grows much faster, but you get a much higher curvature. We grow boron nitride, and it is indeed looks kind of like a high curvature graphite. So it depends really what you want. But you can and these simulations are very fast. This is really just a couple of hours of ND simulations, and you can very quickly look at how temperature and how precursor affects the structure. And then you can do all sorts of fancy analysis. We can, for example, look how rings connect to one another. So we can look at the quality, we can develop quality factors. So if you want to have a 2D material, we can develop a quality factor that kind of indicates that. And then very quickly, we can figure out what is the right temperature. So we can see here, for example, 1500 Kelvin gives reasonable growth. 2000 Kelvin gives better quality. 2500 Kelvin really is too high. Now we really lose control of the quality of our structure. And that's nice information for the experimentalists to work with. And then this was just get phase. Now, if you want to grow on the surface, that's fine. We have actually, within our company, we managed to extend this towards a nickel borate structure, nickel chromium structures. So now we do exactly the same simulation, but we now have a 2D metal available. And you can see that in the previously we saw only a small amount of 2D boron nitride. Now the presence of the nickel really kind of drives the system towards the 2D structure. And we can just very cleanly see at which particular structures occur at which particular time scale. So we start with these really small nuclei. Over time, they mature, and indeed, at the center, at the center of the system, we grow a very nice clean boron nitride. So this type of work then later is getting involved in 2DCC. This actually has been going on. This is a project at Penn State that's been going on for almost 10 years. And so we have developed a very rich database of reactive F description for various 2D materials and their supports. So when you grow these materials, you use various supports, like, for example, alumina, graphite itself, boron nitride, strontium titanate. And so we developed a wide range of reactive descriptions. We have been pretty popular. We have received a fair amount of requests. And most of these are now available in literature. So if any of you want access to those, feel free to send me an email, and I'll be happy to make these force fields available to you. So molybdenum disulfide has been a key target for us. One of the key things that Reactive F is very good at is look at, for example, how curvature of the 2D material affects their properties. So at low curvature, silver defects are unstable. But if you go to high curvature, then certainly these defects can become stable. We can look at the defect stability. We can look at the migration of these defects. Sorry. And then we can look at, for example, how these things grow at complex interfaces. In the left, we have here, for example, oxygen interaction, molybdenum disulfide. We can see how defects react with oxygen. On the right here, we actually grow the molybdenum disulfide on the silica-based force fields. And we see, for example, how the presence of hydroxyl groups can greatly change the deposition. So without the oxide group, you only have sort of localized growth. With the hydroxide group, you get a much, much thicker growth concept. So this is something that we managed to take. So graphite is a very popular growth material. And we found very interestingly that if you grow on a bilayer of material, then the bilayer orientation is a big deal. Whether it's essentially whether they're aligned or whether they're twisted, really changes the way that the 2D material deposits. Because if they are aligned to each other, we get these sort of local curvature. While if you align them differently, you don't get local curvature, but you get kind of more sort of local small curvatures. And these high curvature areas are really nice areas to deposit molybdenum disulfide, because the molybdenum disulfide prefers to bind to these high curvatures. It doesn't bind very strongly, but strong enough to make an early bond, and that's enough to start your growth. And this was indeed confirmed experimentally, where we see that the misoriented graphitic area lead to very, very strong chalcogenide deposition, while the oriented areas have no chalcogenide tungsten disulfide deposition at all. And so our simulations managed to explain this and also give clues to the experimentalists how to use this concept. So this is something that was published in 2023. And then we also looked, for example, how we can interact with gallium deposition. Trimethyl gallium is a very popular gas phase precursor to make essentially gallium metal. And we found actually that if you use graphite as a precursor, to deposit the gallium on, that the state of the graphite is very important. If you have these zigzag edges, you get local sort of clusters of gallium, which is typically not what you want. But if you have armchair edges, you actually get very nice sort of smooth fills of the gallium. And this is the type of gallium deposition that you clearly want. So we can actually control the gallium deposition as a function of the graphite edges. Also, what's very interesting, so one of the goals of this work is actually deposit the gallium underneath the graphite. And so to make that happen, the experimentalists shoot holes in their graphite with oxygen. So they make they make on purpose holes in the graphite so that the trimethyl gallium can get through. And they observed experimentally that it works, but for some reason it stopped working. And what we found in our simulation actually, that the trimethyl gallium can actually repair those holes. So you shoot the holes, but over time, the trimethyl gallium precursor can actually dissociate on the edges of those holes, actually heal the holes. And over time, the concept doesn't work anymore because the holes close themselves and the gallium stops kind of depositing itself in the subsurface. And so now the experimentalists know that they pretty much have to recreate their holes every now and then with oxygen plasma. So this really helped explain many, many issues in the experimental deposition of these materials. We also now have, to connect with physics, we have kind of ignored phonon distribution in the early stage of reactive description, but we recently found out indeed that we can actually get pretty good thermal conductivity. And though that can be important, especially when you have high temperature growth on graphitic materials. So that will lead clearly to local hotspots. And so how fast these hotspots resolve themselves can be very important for material growth. So our new force fields actually do pretty well for thermal conductivity compared to the Stirling-Weber potential, which is very good in that particular area, and also to machine learning-based potentials. Other 2D materials we looked at, this is actually tin selenide. Now, I'll get back to graphite in a second because it's very important for the tin selenide growth. So tin selenide is a very interesting 2D material because it can grow either as a tin monoselenide or as a diselenide. And so we trained our force fields for these things. And we can then do, these are very nice simulations to do. We just have a system of 5,000 atoms. We run it for about a nanosecond and we can see all these initial precursors coming out. We can also see selenium droplets. So this is done at a temperature of about 800 Kelvin. So that's above the melted temperature of selenium. And we can see how those droplets kind of stick to the tin selenide. And we can see how this stoichiometry changes as a function of growth. So in the end, we get up to a stoichiometry of about 1.5, which agrees very well with the experiment. But earlier stoichiometry are much more tin biased. So we see some kind of tin monoselenide growth that eventually becomes a tin diselenide. Now, where graphite comes into play, it turns out that you can actually grow these things also very well on magnesium oxide, but in particular, if you actually add a defect graphitic material on top, so you add a kind of a graphite mask, you can really control the growth much better. So you actually can then, so here's, you see here the dark gray area are essentially a graphene with a big defect. We see now the orange atoms are the selenium atoms, the green atoms are the tin atoms. And we see in 0.1 nanosecond, we see the selenium atoms coming through. We continued it, and we actually grow a very nice sort of pseudo-crystalline tin diselenide, where the selenium likes to bind to the magnesium oxide, and we get a very nice sort of second layer of tin. And the presence of the graphite makes sure that we only grow a single crystallite. We don't grow multiple crystallites, so we get a much higher quality crystal growth. If you compare that with, for example, in the gas phase, it's much more chaotic. We actually get much cleaner growth with the graphite mask than just in the gas phase growth. And we can also, if we just grow the magnesium oxide, we do see some template effect, but we don't seem to be able to control stoichiometry very much. And we get all sort of different cluster sizes at different times. So the graphite mask is very important in essentially controlling our size. Only when we actually use both a graphite mask and a magnesium oxide, we get a very nice crystalline growth. In all other cases, we don't control growth size and we don't control crystal structure terribly well. Finally, I just want to show a new concept. So this is all reactive F work. So reactive F works very well, but one thing it's really bad at is explicit electron transfer. So as we saw earlier on, we really separate out the electronic degree, the weak interaction and the charge transfer completely for the bond order. However, if we transfer charges and transfer a full electron, then clearly the valency of the atom should change, because in CH4-, for example, a carbon has an extra electron, then CH4- is clearly stable for neutral carbon, but it's very unstable for the CH4- radical anion, and it will almost directly break a CH bond, because now carbon is isoelectronic with nitrogen, and for nitrogen, clearly NH3 is more stable than NH4. And so we have developed a E-reactive F concept where we have a limited explicit electron that allows us to communicate between essentially the valency and the number of electrons. So in this case, this carbon gets an extra electron. Reactive F knows that the carbon has 5 electrons, that its valency drops down to 3. So a nice example here is we have here an extra electron in the middle with water. So you see that the water molecules just surround the electrons, they don't absorb the electrons. And so that's the red curve over here. So we have pretty much a sort of a physical interaction. This is a dissolved electron, which indeed is absorbed experimentally, and these things have a very long lifetimes. If we are, however, at an OH radical, so now I remove the hydrogen, and you see after a while the electron finds the OH radical and turns it into an OH anion. And we see indeed energy release. These simulations are very fast, so doing this with DFT is very expensive because you have to do time-dependent DFT, and it typically can take you several weeks to do this type of simulation. This simulation in reactive only takes about 40 seconds. So coming back to graphite, we managed to develop this a couple of years ago for the lithium graphite system for batteries, where we actually can really simulate the electron transfer at anode. So we start here at the bottom with a graphitic anode. So every carbon has 1 electron. We add 1 extra electron in the graphite. So this is essentially a -1 graphite. The lithium cation here in pink comes close to the graphite. So this is a lithium plus. And then after a little while, that extra electron finds the lithium and jumps to the lithium, makes a neutral lithium. And now this neutral lithium can make lithium metal. So we have a real electron transfer event now, and that's clearly very important. And now we also can do voltages, because we can simply add more extra electrons to the graphite and allow them to move through the graphitic material. So this was developed against a pretty big training set with all sort of polyaromatic hydrocarbons, where we included the electron affinity and ionization potential. We also trained it against in-plane conduction and out-of-plane conduction in graphite, and against basic sort of graphite equation of states. And then we managed to actually simulate indeed electron. So we can actually do a concept of electron mobility. So I just, to guide your eyes, the extra electron here is colored in red. It's really in the same electron as all the other electrons. We can see it can hop around in the 2D direction. And over time, it really looks like the DFT picture. So the extra electron is really pretty much has an equal capability to be everywhere in the lattice, which is clearly what you expect to see. But also it only pretty much moves in the 2D plane. It doesn't move in the 3D plane. In graphite, it doesn't hop between the layers. It just stays located in the 2D direction. So this was published in 2022, as you see here below. But also now we can do more complex things. If we, for example, add a defect, we see that over time, the extra electron actually localizes around the defect, and that's indeed in good agreement with DFT. And if we now, for example, look at graphite, and we force, for example, we make an sp3 linker, so we pretty much make a defect in the graphite, very slowly, the electrons can now move across that sp3 linker, and sort of over time, they eventually are now in both layers. But you see, this actually is pretty slow. It primarily moved in the sort of the electron-rich layer, but then over time, it can move to the second layer. And so now we can actually start doing simulations, actually look what really happens in a battery. We can have, for example, multiple lithium atoms. They can abstract, now the lithium atoms, when they initially are ions, they essentially don't interact with each other, so they stay as far away from it as they can. But when they actually start grabbing electrons, they become neutral lithium, and the neutral lithium can start making a lithium metal. And this is reversible. I can now, for example, also reverse this. I can take electrons out of my graphite. The graphite will then start stealing electrons back from the lithium. The lithium becomes lithium plus, and it will start dissolving in the electrolyte. So you can really now doing real sort of battery cycling at the react level. Okay, I hope this gave you some examples of what reactive F capability is. So we have a wide range of materials available. We can essentially make interfaces between these materials, and we can do relatively large-scale simulations. So we can easily scale these things to, if necessary, over 1 million atoms. We can typically put about, very comfortably with AMS and LAMPs, you can put about 10,000 atoms on one core. So you can kind of figure out how big you can make this. And now with E-reactive F, you actually can add even an explicit electron concept where you can do sort of simulations that address electron conductivity to some extent. So thank you very much for your attention. I'll be very happy to take your questions.
Professor Duin, thank you very much for excellent presentation. I learned a lot. So questions from the audience? Please address it directly to Professor Duin. Well, I'll start.
Oh, I was going to ask.
Okay, so Carter, do you have a question? You want to go ahead?
Yeah, I was going to ask. First of all, great talk. I really wanted to say that your insights helped me a lot with my own work, because I do work with.
Oops, you went.
Yeah.
You muted yourself in the middle.
Carter, we can't hear you.
Oh, can you hear me now?
Yep, I can hear you now.
Apologies. I was saying you really have helped with my some insight into how I want to take my work forward. I've been thinking a lot about building databases for these kind of structures that you're generating. Have you kind of thought about pushing, especially for like the carbon community as a whole, to kind of have some place that we can go and look at, oh, this is these interactions we're building, these are some structures we're generating. Do you have any insights on that? I know you've worked with a 2D material database, as you mentioned in the slides.
Yeah, we used, in my group, we used the material project database quite extensively, which is clearly a DFT-based database, but at least it gives you all the crystal structures, and that's something that we start. Now, I do agree there's nothing that really goes beyond that. Now, there might be other graphene communities that can store structures. Now, my group has databases for force fields. And we actually they are effectively, so any sort of request to MCC, you always get a positive response. If you need a force field, just email the MCC, I'll send it to you. We're now actually putting all these 2D-based databases. We put them on the 2DCC project at Penn State has a online database called Lists that they use to store all the experimental samples, and we're currently extending that to also extend that to simulation samples. So that will be force fields, but it also will be structures associated with force fields. So, maybe publish stuff. Typically the supplementary information doesn't give you all you need. We really want to extend beyond that, and we make all the input structures that we use in our simulations available through the LIST framework. So this is something that we're currently developing. I'll be happy to keep this community up to date about how that process goes. But for now, any published force field that you see that you want access to, just send an email to the Material Computation Center websites, and I will essentially send you that force field.
Awesome. Thank you so much. That's super helpful.
So another question, Professor Duin. So I think you mentioned with regard to neural network-based potentials, interesting weaknesses. Could you just maybe give us?
It's not completely my field, although I do talk extensively. And now I just want to get this out there they are extremely useful. Yeah, I'm nothing against neural network-based potentials. They have a very good spot in our multi-scale simulation frame. One thing is, since they're not physics-based, they repeat very well what they've been trained for, but there's no mathematical assurance that they transfer beyond their training set. So Reactive F is physics-based. If you train against stuff, you still have a pretty good chance it will work for a slightly different material. It will lose accuracy, but it will not fail abysmally. For example, let me give a practical example that I know a bit about. We try to use the CHG net for silicon carbide evaporation. CHG net worked extremely well for silicon carbide crystals because it was trained against that. But when we evaporated the silicon carbide, it gave very bizarre results. It told us, for example, that silicon 2 does not exist. It told that it has a cohesive energy of 0. Now, that's fine. I mean, it wasn't trained for it. But with Reactive F, you never get that sort of issues. It will always at least give you a somewhat reasonable result. So the transferability of neural network potential is much smaller than for physics-based potentials. Also, in principle, physics-based potentials should be faster than neural network-based potentials, because the only way the neural network-based potentials are so accurate is because they have almost infinite amount of equations available. With physics-based potential, you have a much more condensed phase set of equations. So a high accuracy neural network-based potential, it will be more accurate than Reactive F because, you know, it has many more equations available, and it can always open up more equations if it needs them, while Reactive F has a fixed set of equations. So you get better accuracy, but you get typically slower speed, and you never quite know that transferability. One pet peeve that I have against the neural network-based community, I rarely see them talk about transition states and real gamma. They just use millions of data points, and they say, okay, now we have the chemical space. I really would like to urge that community, and they're doing, some of them doing that, but to really go back to, you know, things that chemists care about, talk about transition state, talk about energy barriers, because that's really, to me, the sort of thing that they need to do to make them, you know, better appreciated by a wider community.
Is it possible that the neural networks could be trained to look at energy barriers in the transition state?
Yes, I've actually worked with a group from Cambridge, and we actually had a paper out this year where they actually explicitly, you can train them against it, but you have to train you cannot just train against random clouds of data. You actually have to start putting that transition state energy data in your training set. And that's something that many people in the neural network community are hesitant to do, because they say, we really would like to just do a whole bunch of AIMD and just put the data without any sort of further treatment into our training set, because that's nice for the developer. Yeah, if you don't have to worry about the chemistry, it's easier to develop it. But I'm telling you, you do need to care about that chemistry. You do need to care, because if you make 4 million data points but you don't get a transition state right, you're still not going to get the right kinetics.
Excellent.
So anyway, that's a communication, and if people are on board here that love to communicate, I love to communicate with the neural network-based community, because I think there are some very good things happening in that community that I think also my group is learning from.
Question from the audience?
Hello, Professor.
Hello.
I'm Xian, and I work with Professor Wang, and I have my question about my own research work.
Sure.
So my research is focused on the bipolar electrochemistry isolation of the graphene, so which allows us to fabricate the graphene electrode in a one-step process. So as part of my work, I'm using COMSOL and the DFT simulation to study the influence of the temperature on the reaction rate. So just covering both the isolation and the deposition process. So currently, I estimate the relationship between the current density and the amount of the isolated carbon atom out by analyzing the energy state at different stage of the ion integration or the isolated part. So I noticed that your research involves the growth and the defect formation and the oxidation of 2D materials. So I was wondering if you have any suggestion on how I may incorporate this aspect into my study to develop a more comprehensive understanding of the BP system.
Yeah, that's a really good question. It's a bit hard to give a full answer, and I'll be happy to communicate a bit more by email with you. But the electron density is something that I think we are currently trying to experiment, doing somewhat similar simulations, using and see how excess electrons in E-reactive F can change growth kinetics of graphite. So I think that reactive F can certainly do solvent effects and things like that, but it really cannot do charge density in a credible way. So that's one of the reasons why we developed E-reactive to start with. So it may be that some of the E-reactive F capability might be very relevant for your work, and I'll be happy to communicate further with you on that.
Yes, I really appreciate your presentation, because you really give me a more soft. Yeah.
Sure. Thank you very much for your question.
Yeah, I'm Chunlei Wang. I really appreciate your talk. Very interesting talk. We are also interested in graphene phosphorin heterostructures.
Okay.
That may be more interesting because
that's a good point. Yeah, there's actually a really good phosphorus. My group didn't do that. There was a group in China that developed a really good phosphorus description. So that should actually be a pretty good combination. I don't know what you need. What I don't know is how much interaction between carbon and phosphorus you need for that. But that could certainly be a good interaction to go to.
Yeah, and I'm also interested in if the can localize the redox reaction be selectively triggered, and if we can solve some problem like especially resolve the deposition inflation issue, that will be super interesting for me.
Yeah,
thank you.
I need to understand the precursors a little bit more of that, and also, but I think typically these force fields can be combined pretty well. The one thing that I need to understand, I just don't know by now, is how the chemical interaction between the carbon and the phosphorus work in that. But if you have some ideas about that, I'll be very happy to communicate with you on that.
Yeah, we experimentally we can synthesize graphene phosphorine from the bipolar electrochemistry using DI water. We didn't look into different electrolytes yet, aqueous, ionic liquid, pH, etc. But that's really deserve a lot of attention in that field.
Yeah, no, that's at least we can very easily put those materials together in one simulation. So that will be an interesting target for sure.
Thank you.
May I ask maybe the last question?
Please go ahead.
In your opinion, can the phosphate method be combined with DFT? I mean, for example, if you get the ground configuration of the system, can you use this configuration as an input for DFT method? How reliable is, not reliable, how transferable is force field as input into DFT to get all the electronic properties within charge there?
Yeah, so reactive F has a much more limited electronic property. The standard reactive F only has a point charge, and that's all it has. So it doesn't have clearly a more complex electron cloud. E-reactive F has a slightly more complex structure because you have actually an electron nucleus dipole at least, but that's still not as complex as DFT would make it. But I think it works reasonably well. Now, you can also do hybrids between reactive F and DFT, of course. You can do QMMM with a regular force field, but QMM with reactive F is probably a little bit easier to do for DFT because at least you can do some concept of charge transfer. We have managed to make hybrids between reactive F and non-reactive force fields, which work very well. But similar hybrids can probably be made between DFT and reactive F. Not sure that completely answers your question.
To some extent, so you are getting kind of the ground configuration, right?
Yeah.
Of the system.
Yeah.
Can this ground configuration it be used as an input for DFT?
Yes, I mean, sure. That's actually a game that we play out of. As long as the atom positions are sufficient information for DFT, then that's actually something that we do quite extensively in both the force field training and other states. So quite often, for example, if you want to get a band spectrum for a complex material, then we use reactive F to predict the material structure, and then we go back to DFT to calculate to calculate band gaps and things like that. Because reactive F clearly doesn't have access to band gaps. But that sort of transfer between reactive F and DFT we do quite extensively. Now, sometimes the reactive F structure may not be exactly the DFT structure, but typically with just a little bit of energy minimization, you can turn it into a pretty reasonable DFT structure.
Okay, yes, that's it.
Yeah. So the React structure will not be exactly the DFT structure, but it will typically be a pretty good guess.
Okay, thank you.
Yeah.
So it's 10:59 East Coast time. I think we have time for one more question. Professor Duin, I want to ask him on behalf of a number of young scholars here in this platforms, where do you see this field, molecular dynamics, going in the next 5 years?
Yeah, 5. That's an interesting time frame. Yeah. I think it is our target is to really turn from, and that I mentioned in the beginning, it's good to explain experimental successes. That's great. But we should really get to a stage, maybe it's 5 years, thereabout, that we actually should actively lead experiments and really tell it not only. Now, machine learning is really good at predicting new materials combination, but it doesn't tell you synthesizability.
Mm-hmm.
And that's something where these reactive force fields can be tremendously helpful. And if we really get them accurate enough to predict, is there a temperature compositional windows where these materials can be synthesized? And how does the quality of the synthesis change at the function of, the typical experimental renders, temperature, pressure, that sort of stuff? I think this ability is beginning to emerge. And so there's so much need for new materials everywhere. I mean, I primarily work in semiconductors, but everywhere you look around, there is an enormous need for new materials that do everything 2 times, 3 times, 5 times, 10 times better. I think these simulations can play a crucial role at finding new, and also humanity cannot afford to wait 50 years for those new materials. We need them in 2 years. We need them in 5 years. And I think that's something that we have now that we didn't have 40 years ago. We actually can use these theory tools to test out if these things are synthesizable and really help the experimentalists with the synthesis of them. So that, to me, is the sort of the crucial thing to push forward.
Excellent point. I think that's a perfect way of ending a very interesting talk. Professor Duin, we really appreciate you. And I ask the audience to give a round of applause just to appreciate the talk. Thank you very much.
My pleasure entirely. Thank you so much.
Excellent. So now we go to the next speaker. I've noticed Professor Feliciano Giustino is on board. Good morning to you, sir. Would like to introduce Professor Giustino. Professor Feliciano Giustino is a professor of physics and holds the W.A. Tex Moncrief Junior Chair in Quantum Materials Engineering at University of Texas, Austin. He earned his PhD in physics at École Polytechnique Fédérale de Lausanne, EPFL, as you guys know, Switzerland, and held a postdoctoral appointment at the University of California, Berkeley. And during 2008 to 2019, he was professor of materials at the University of Oxford, the UK. In 2017 to 2018, he was the Mary Shepard Upson visiting professor in engineering at Cornell University. He's also the recipient of a Leverhulme Research Leadership Award, 2019 Clarivet Analytics Highly Cited Researcher, and a fellow of the American Physical Society. He specializes in electronic structural theory, high-performance computing, and the atomic scale design of advanced materials using quantum mechanics. He's authored over 130 scientific publications and 1 book on density functional theory. And he works on material design, which has led to the discovery of several new semiconductors for applications, energy, and optoelectronics. With that introduction, Professor Giustino, it's all yours.
Well, is it okay to record?
Of course, yeah.
Okay, perfect.
Thank you, Sam, for the kind introduction, and good morning, everybody. So maybe let me share my screen if I can. Can you see my screen and
Yes.
my pointer?
Yes.
Okay, fantastic. So let me just hide my all right. So again, good morning, everybody. My name is Feliciano Giustino, and I'm with the University of Texas, Austin. So today I've been asked to give you a little bit of a perspective on ab initio materials design. So this is going to be, I would say, rather complementary to the previous talk by Professor Van Duin. And what I'm going to do is basically to introduce my group and then introduce a little bit the world of density functional theory and beyond, and then show you a couple of applications. Disclaimer, we're not really working on carbon materials or synthesis, but we're more in the world of high performance electronics or photovoltaics. So bear with me while I share some of these advances. So first of all, where are we based? I'm basically calling in from the University of Texas, Austin. So UT Austin is pretty much in the center of Texas and is the flagship university of the University of Texas system. At UT, I'm both with the Department of Physics and with something called the Oden Institute for Computational Engineering and Sciences, which is this building pretty much in the center of campus. I'm bringing this up because in the Oden Institute, the way we work is that all of us have joint appointments between a department and the institute, and we work in areas going from material science to physics to astrophysics to engineering to computer science. The common denominator is that everybody is very invested in applied mathematics and high performance computing and software development. And in addition to that, UT Austin is the home of TAC. So TAC stands for Texas Advanced Computing Center. So this is the flagship computing facility of the National Science Foundation, for those who are not aware of it. And what you're seeing here at the bottom right, this is basically the SEBI data center, which is 3 miles north of campus, where TAC will host the next leadership class supercomputers of the National Science Foundation. So this is going to be called Horizon, and it's a machine that is worth about $500 million, and it's going to come up maybe next year. So within this context, my group does 3 things. So the first interest is that we want to work on the quantum theory of materials. We really started from condensed matter physics, but they were broadening up towards material science. And quantum theory just means that we are very much interested in the electronic properties, in the wave functions and quantum mechanical methods. The second thing is that to do this, we use and we develop tools that are to be used with high-performance computers. So this is a picture of the Frontera supercomputer that I took last year. This is from TAC, the Texas Advanced Computing Center, and this is the current large supercomputers we have here. And a lot of the time in the group is spent developing software. Okay, so trying to write software that will be more performing and then allow us to do better calculations. So ultimately, the goal is to do 2 things. One is to support experimental colleagues in the interpretation of the data. But the second one, maybe more ambitious, is to try and come up with predictions of new materials. And I will show you in the talk that this sometimes is successful. In fact, the powder sample you see in this vial here is something that we predicted has been synthesized. I will come back to that in a second. So the talk is structured in 3 parts. So in the first one, I would like to maybe give a very brief introduction on what it means to model materials using quantum mechanics. And this is pretty much an introduction, a very brief introduction to density functional theory and how we see it today. And then I will give you a couple of applications about working in my group, and then discuss a little bit about software and then where the cyber infrastructure is moving in this field. So let's get started with using quantum mechanics for materials. So these slides are 2 slides just to kind of give you a perspective on how significant has been the impact of techniques based on density functional theory in the world of material science. Actually, this is a picture from a paper that was published in 2014 by Richard Van Noorden. Richard is an editor at Nature, and at the time I just wrote a book on DFT. So he called me to discuss some of the findings that they had. What he did here is to look at all papers published by mankind, and all those available, and then rank them by citation metrics. And they looked at the top 10 papers. So if you zoom in the top 10, what they discover is that number 7 and 8 were 2 papers that have to do with the foundations of density functional theory. All of the other papers have to do with either genetics or medicine. And this is really about citations and ranking across all disciplines of knowledge. Okay, so this is just to give you an idea of how impactful this has been in current science. The interesting bit is that as you all know, in the past maybe 10-15 years, there's been the rise of AI and machine learning, and all of these papers are extremely well cited because they are very useful. They are used by many groups. So one might wonder whether DFT has lost its place in the top 10. And actually, I was surprised to discover that just a couple of months ago, the same model, so Richard Van Noorden, published an update of that list. So this is from 2025. Again, looking at the top 10 papers. And the interesting bit is that you see one paper from, in the field of AI. So this is one of the foundational work on deep neural networks. But now, instead of having 2 papers on DFT, there are 3 papers on DFT. In fact, the one in the middle, actually, this one here is basically the paper reference for the code VASP, which is one of the most popular software for density functional theory calculations. So this is just to say that even though there is a huge attention and interest in AI and very large communities, DFT continues to play a very significant role in the field. Now, so what does it mean to perform calculations at the level of using quantum mechanics? So the idea is very simple. So this is what you see in the middle here is the many-body Schrödinger's equation. The lowercase indices refer to electrons, and the uppercase refer to nuclei. So you have kinetic energy on this side. Then you have the repulsion between electrons here, repulsion between nuclei, and the attraction between electron and nuclei. So this is the core Hamiltonian that one would like to study. And if you are able to solve this Hamiltonian and find the total energy and the wave function, I think you probably will know a lot about materials. Of course, as you can guess, this is not doable. In fact, there are no solutions to this equation as of now. And people have to resort to approximations. So the main challenge with this kind of equation is really in the scaling. So one can just do some simple math to show that this wave function, so the amount of information contained in this wave function grows exponentially with the number of atoms or electrons in the system. So this exponential scaling actually is a curse in the sense that it makes it very difficult to do these calculations. And it's also a boon in the sense that it's precisely what makes quantum computing appealing. So density functional theory is a theoretical device that allows one to reduce the complexity of this problem to something more manageable. And of course, that comes as a price, and the price is that the calculations are not exact, but they have approximations. So in practice, what the density functional theory does, in a nutshell, is the following. Instead of trying to solve for a wave function that depends on all of the coordinates of every particle, it basically tries to solve for a lot of Schrödinger's equations for wave functions of a single particle, in this case, an electron. So this is no more difficult than any textbook exercise in quantum mechanics, this equation. The only challenge is that you have this potential called self-consistent field potential, which at this stage is unknown. So one makes a guess for this potential, tries to solve for this equation, and then from the solution, one builds the density of electrons in this case, which is just the sum of the square moduli of the occupied electronic states. So where does density functional theory come in? Density functional theory tells us that once you have this density, you can build the potential that we need up here using a simple protocol. And that basically consists of incorporating this density here in an electrostatic term, which is called the Hartree energy, and then here into another term, which is called the exchange and correlation energy. Now, we don't know really an exact expression for these objects, but there are very good approximations that have been developed over the past decades. So once you have this potential, you can go back and plug it back into the original equation, and then you solve it again. And basically, this loop is solved until nothing changes anymore. The advantage of this operation is that instead of scaling exponentially with the size of the system, now the computational effort scales with the cube of the number of atoms. And that's a significant gain. And that's what makes calculations including tens, hundreds, thousands, and even 10,000s of atoms feasible nowadays. So that's pretty much where the nutshell of DFT calculations. And of course, we will not have time to go through the details, but I just want to mention that if you're interested in the basics, just to understand some of the key ideas, as I mentioned earlier, 10 years ago, I wrote a little book that was really meant for my students when I was at Oxford. So this is for final year, senior year undergraduates and for first year PhD students. So there is no requirements of advanced quantum mechanics. And if you want to dig deeper, there is a classic textbook that is by Richard Martin, who's a pioneer in the field. And this will contain everything any expert needs to know about this kind of techniques. And then if you really want to contribute to the foundational developments in this field, I would recommend this book by Parren Yang, who really goes into the mathematical aspects of the problem and what one needs to know to really make further progress. So just to give you an idea, actual density functional theory now is no longer something that belongs to a specialist kind of community. It is entering a standard graduate program and undergraduate programs. So for example, next fall here at UT, I will be teaching a course which is entirely devoted on density functional theory. This is for first year grad students. It starts from physics, but we admit students from every department, from mechanical engineering to electrical engineering to chemistry and so on. So this is really becoming something that will be probably part of the standard curriculum of many STEM disciplines, over the next few years. And the interesting thing about this kind of courses also is that they can be made in a very interactive way. So we usually have sessions, live sessions at the Texas Advanced Computing Center where people learn by actually performing calculations by themselves. So another thing I want to mention about methodology, and this was brought up during questions at the end of the previous talk, is that there is a lot of work now that's going on in this area in the world of machine learned interatomic potentials. And this is not something I want to focus in this talk, but just to give you an idea of what is happening there. The idea is basically that in density functional theory, when you determine the total energy, this is really a function of the coordinates of all the nuclei and of the atomic species. So you can imagine, you can see this as a functional mapping between the structure and the chemical composition and the total energy. So since it's a functional mapping, it makes sense to try and use universal functional approximators like neural networks in order to learn this mapping. And this is what many groups have been doing in the past few years. So the idea is to start from a bunch of structures that you can generate either by random sampling or by molecular dynamics, and then transform the structure into basically a vector of numbers. So this is what is going to be fed to the input layer of the network. And then you will try to optimize the weights and biases in this network in order to produce a number at the end which matches the DFT total energy as closely as possible. So now there is an enormous amount of work in this area, and I just want to mention that there is so much work that is already a lot of standardization effort going on. For example, these two snapshots, I took them yesterday from the MathBench Discovery portal. So I'm sure everybody is familiar with the materials project. So the same group has put together this benchmarking kind of operation. So what they do here is to take any new proposed force field, so machine learning force field in the literature, and run it through the materials project database and collect statistics on the errors. So this is what is called the MathBench leaderboard that you see here. And then have a graphical visualization of which of these machine learning force fields performs better according to specific metrics you might be interested in. So actually, I would encourage you, clicking on this link, because all these graphs are very interactive and very instructive. And this is actually being updated live because these models have been generated at a very fast pace. And that's a very good reference for if you want to use any of these techniques. Now, let me tell you a little bit about a couple of applications that we've been working on in my group. So this is really specific to a couple of areas where we've been very active. So one is about really electronics, so electronics, beyond silicon, and the other one is about developing new materials for high performance photovoltaics. So if I start with electronics, I'll basically explain the problem and then give you our kind of proposal for possible solutions. I know that some of you may not be familiar with this topic, so this is a mini crash course on where we stand with, let's say, transistors. So the main kind of element of all of the chips that we use today, so all the current electronics, is called the field effect transistor. So what you see here is a textbook representation of the planar field effect transistor from this recent book by Professor Jenna Cornell. So what this is the gray area is a semiconductor, usually silicon. S stands for source and D for drain. So what happens is that you place a voltage between source and drain, and you drive a current. Okay. Now this current is controlled by the application of a voltage through this other green part, which is the gate. And in practice, the gate voltage acts as a valve in order to control the flow current, and this is what allows you to perform logic operations. So once you power this device, you have a current voltage curve that looks more or less like that. So a significant drain source voltage, you can control the current here by moving this plateau via the gate potential. Now, the important part in this story is that in order to make the transistor more efficient, meaning that you can switch it with a lower potential and it generates less resistive losses, you need to basically improve this single device descriptor, which is the carrier mobility. So this simple parameter mu is a materials level parameter, and it is actually a descriptor of how fast electrons can move in a semiconductor once you apply an electric field, okay? So it is important to have this number as high as possible. So what has been happening in the past 50 years in transistor design? So on the left, you see what I just showed you, the textbook model. So this model does not exist today, essentially. Was from half a century ago. So since maybe more than a decade, most chips use the FinFET, where the channel, so this gray part, has been elevated, and it looks like a fin, and is surrounded by the gate on three sides. So this is because the channel is becoming thinner, shorter, because people want to pack more transistors in the same chip. And to allow for better electrostatic control inside this channel, you need to have the gate, surrounding it. And since, 3-4 years now, we have a further evolution of this concept, which is the gate all-around field effect transistor, or ribbon FET. So this is either TSMC or Intel. And it's basically a architecture where now the channel is surrounded on four sides by the gate. And it has really become a set of maybe nanoslabs that pierce through this gate structure. So this is pretty much what we are using today, and probably if you are holding an iPhone in your hands, this is kind of architecture is what you're using. So why I'm showing you this? What has been happening, in order to go from the left to the right, the thickness of these layers have been going down in order to allow for lateral scaling. And this poses a problem. So these are a very old experiment that has been, is kind of considered a classic in the field. And what people have done is to study the mobility, this basically the transport of electrons, as you thin down this channel. And this is the results. So you see the mobility as a function of thickness goes down as you make the transistor, so channel thinner and thinner. So once you reach the nanometer scale, 1 to 3 nanometers, the mobility goes from 1,500, which is bulk silicon, to less than 100. So this leads to a very significant increase of losses and Joule heating. So that's something people don't want. So why this is happening? This is happening because at this nanometer scale, most of the electrons travel very, very close to the interfaces and experience scattering from interface inhomogeneities like roughness and defects. So the community that is interested in developing post-silicon devices has been essentially focusing primarily on the possibility of using two-dimensional materials to replace silicon. So this is only a cartoon, but it illustrates the main idea. So in 2D materials, like van der Waals materials, like in this case, molybdenum sulfide, what is happening is that you can realize these materials in monolayer form, and therefore you can have atomically smooth surfaces. And there is the hope that because of that, the interface scattering may be suppressed, and therefore you might have still reasonable mobilities without having experienced the degradation that people see for silicon. So this is the concept, and 2D materials have been around since 2004, and 20 years later, actually nobody has still as yet found a 2D material that can rival silicon in terms of carrier mobility in real channels. So despite the promise of 2D materials, there is still a problem in identifying actual materials that will work in real transistors. So in this area, what we've been doing is to collaborate with experimentalists and companies in order to come up with proposals for potential 2D materials that might fit the bill and deliver the sought after high electron mobilities. So in this slide, what I'm showing you is just a couple of benchmark calculations. So these are calculations of the carrier mobility in silicon on the left and other standard semiconductors performed from first principles. So what does that mean? We solve the so-called Boltzmann transport equation, which is a standard equation in semiconductor physics. The difference with respect to what was done 20 years ago is that all of the parameters, like the electron band structures, the phonon band structures, the electron phonon coupling matrix elements, all of those are generated from first principles using either density functional theory or density functional perturbation theory, or quasi-particle GW methods, which are a little bit more accurate. And the figure on the left shows you a comparison between the experimental data, which are the yellow symbols, and our calculations, which are in red. And I would like to emphasize that the calculations do not include any fitting parameters. So the only input in these calculations is the atomic mass of silicon and the atomic charge. And you can see that the agreement is pretty spectacular in this case. And that basically tells you how predictive now these kind of calculations have become over the past few years. Now, silicon is a little bit the best case scenario. If you look at other materials, the agreement is not as perfect. We tend to slightly overestimate the mobilities that are seen in experiments, but we're really talking about overestimation of the order of maybe 30%. And the mobility values, they really sweep many, many orders of magnitude. So a 30% agreement, we think, is good enough for, let's say, materials design. So based on that, what we need is, to try and screen large materials databases to potentially identify 2D materials with high mobility. And in this field, there's been several databases put forward by the community. So we chose to start with the one put out by the group of Marzari at EPFL Lausanne, where basically they identified about 5,000 materials that can be exfoliated. And then out of that, we applied a hierarchical high-throughput screening approach, where basically you start performing simple calculations for all of the materials. And then you use this simple calculation to kind of narrow down the list of candidates. And then you perform a little bit more advanced calculations, and you keep narrowing down. And then when you reach the bottom tier, what you're doing is you're doing your most advanced calculations for maybe a dozen, 10 to 20 compounds. And just to give you a sense of the complexity, a calculation of carrier mobility at the highest level today is not something that you can do on a desktop in a few minutes. This is something that usually requires high performance computing, and maybe one calculation will require 1 or 2 weeks of supercomputing time. So with this, we did a lot of work in terms of performing these high throughput calculations, and I'm just going to give you the final result in the interest of time. So even though we consider many compounds that some of them even not yet synthesized, it turns out that our calculations brought us back to a compound which is tungsten diselenide, which is pretty common in the world of two-dimensional materials. So it turns out that our framework predicted that this compound should exhibit a carrier mobility in the range of 1,000 centimeters squared per volt second, which would be extraordinary for transistor applications. And it's actually a little bit at odds with what was reported in the literature, where people could not reach anything about 200 centimeters per volt second. So there was a bit of a discrepancy. When we published this result, we got a little bit of a pushback, essentially telling us that maybe our calculations were, were just kind of inaccurate and not able to predict experiments. However, as soon as we incorporated, the effects of impurities in the sample, the mobility dropped from 1,000 to about 50, and this is much more in line with what has been observed. So the main message here was that if you perform calculations in the pure sample, you get some extraordinarily high values of mobility. And as soon as you incorporate impurities, this drops down to very poor mobilities. So the message is actually that if you want to achieve high mobility, one should focus on this material and on making it as pure as possible. And this is not just a fantasy. Actually, last year, at the same time as when we made these predictions, the groups of Phil Kim at Harvard and Corey Dean at Columbia, they actually managed to synthesize tungsten diselenide with an impurity content of less than 10 to the 10 centimeter per centimeter square. With that, they achieved mobilities in the order of 1,000 centimeters square per volt second. So actually, that was in incredible agreement with what we predicted. So now there is experimental colleagues of ours who are actually pushing forward to try and replicate those data and try to make pure samples of this compound. This seems to be one of the most performing materials in terms of transport, at least theoretically. It is just an example of how calculations sometimes, even if they go against the mainstream, they may contain some elements of reality, and it might be worth, maybe they could be used to motivate further experiments and to push maybe a direction that was maybe shelved because the initial results were not very promising. Now, let me tell you a little bit about the second topic, which was, solar cells. This is basically a schematic of a solar cell. So it's extremely simplified, of course. So that is that the light comes in, and there is a light absorbing layer. This is denoted as perovskites, in this case. In this layer, the light generates electron and holes, and those can be collected, the electrons by maybe a negative electrode, so the titania, and the holes by this organic spirometers on the other side, and this generates an electrical current. Now, there is a lot of work on solar cells, and we have an immensity of data points from many devices collected over half a century. So this is actually a table that is updated regularly by the National Renewable Energy Lab. It shows the solar cell energy conversion efficiency versus the year of introduction of a given technology. So the efficiency is basically how much power you can get out of the solar cell for a given input power from sunlight. And if you're wondering, the standard silicon solar cells are these kind of blue lines in the middle that reach something of the order of 27% at this point, 26-27% efficiency, and that's what you have on rooftops. So silicon has been developed for half a century already, and I would like to focus on these new compounds here that came up in 2012. So these are called perovskite solar cells, and then now they reached something of the order of already 26% as a single layer, and 29% in tandem devices. So these is an enormous research field with many researchers and thousands and thousands of publications every year. And in this field, we are basically also trying to contribute in the area of design of new materials, as I will show you in a second. So this structure here is the, let's say, the prototypical lead halide perovskite. What this structure is showing is lead in the center of the octahedra, iodine at the corners, and this molecule in the middle is metal ammonium. So this is the first and the prototypical kind of halide perovskite in solar cells. Today, the structure is not exactly this one. There is a much more complex composition that people have been optimizing over 10 years now. But most of the physics and it's kind of contained, represented by this kind of structure. One of the main concerns in the early stages of research in this field is that these kind of systems are very performing, but are also very unstable. So what that means is that after you have this compound in a solar cell, it may degrade, and that may release lead in the environment. So that's something that people don't like. So what we've been working on is trying to ask the question of whether we could find compounds that actually are as efficient as these solar cells, but they don't contain any lead. And the key idea here is that this compound is partly ionic, and the lead is in 2+ oxidation state in this system. So what we did to start with is to search for any other 2+ element in the periodic table that could replace lead and give us a stable and compound that would also be useful in terms of optoelectronic applications. And the result of that work was that we did not find anything. Now we moved on to something a little bit more complex, but still doable, which was to consider that instead of replacing just one lead element, you may try to replace 2 lead atoms. Instead of having a 2+, you could have a 1+ and a 3+. For example, you could have something like silver on this side, and you could have bismuth on this side, and the total charge neutrality is maintained. And the other thing we did is to replace the organic molecules, which are actually responsible for a lot of the instability in the system, by simple elemental cations. And we performed a study of any possible combinations of these materials that you could form in this kind of stoichiometry. So this is just a summary of what we found. These diagrams show you basically the density functional theory, decomposition energies of some of these compounds. And in particular, this is cesium-2, bismuth. B prime is a noble metal, and X is either chlorine, bromine, or iodine. So whenever these data points are below the 0, it means that the compound is unstable towards the decomposition into some byproducts of these kind of elements. And whenever the data points are above 0, it means that the compound does not want to decompose, and it will be stable. So what we learned from this, maybe just focusing on the left picture, is that whenever you have silver, you have some hope of replacing lead in these cases. And this will work most likely with bromine and chlorine because this is the region where we are mostly positive. So these simple observations based on total energy calculations has led us to the prediction of a few compounds that should be stable and should have interesting optoelectronic properties. And actually, these compounds were synthesized by our collaborators when I was then at the University of Oxford. So this would be the group of Professor Nate, who is one of the discoverers of perovskite solar cells. And the compounds in question are the silver bismuth halides. So these are silver bismuth chloride, silver bismuth bromide, also an indium silver chloride. And later we also found an oxide perovskite where the indium surprisingly acts as a high charge cation. Now, these compounds, you see that they're all kind of powder samples, so they may look like nothing, but these are really the pictures from the original discoveries. And as you know, whenever you know that a compound can be made, then it is not impossible to maybe grow it and make it in larger single crystals and things like that. So the good news is that many of these compounds now are used by many labs. They've been studied in many studies. Maybe the most striking result is that for this one that originally was really maybe the one that we had the least hopes, just 1 year after we made the prediction, the group of Jantan actually demonstrated that this compound can be made in extremely high-performing LED devices. In practice, this compound emits warm white light with near unity quantum efficiency, and therefore it can be used to make LEDs where you don't need to combine red, green, and blue to get white light, but you have a single material that already produces white light by itself. So this actually now is a completely new research direction with many groups working not on the photovoltaic properties, which are not great for this material, but on the ability to use it as a light emitter. So that's also one case where actually we were searching for photovoltaics and we found an LED system, which is something that is serendipitous, but is the important is really the result, and that's very interesting. Let me also mention maybe something more recent where we kept searching for perovskites that could be of interest for optoelectronics. And instead of staying with halide perovskites, so we tried to look for different anions. And in particular, we went to nitrides because there are barely a handful of nitride perovskites reported ever in the experimental literature. So we did a lot of work to try to look at the decomposition pathways of some of these nitrides. And we found that the cerium tantalum nitride was basically a possible candidate for a new nitride-based perovskite that would also be a good semiconductor because the band gap is of the order of 1 electron volt. And the other thing is that these semiconductors appears to exhibit some incipient ferroelectricity that comes out from the calculations. So the interesting story in this work that was from 3 years ago is that when we sent it out for review, we got a lot of pushback from the referees and even from the editor because they told us that this compound would require cerium to be in the +4 oxidation state, which is next to impossible because nitrogen has to be -3, so this would be -9, tantalum is +5, so the cerium would have to be +4, but it usually likes to be +3. So actually we had a hard time to publish this work, but in the end we managed, and just recently, a group at the Chinese Academy of Sciences demonstrated the synthesis of this compound exactly the way we predicted it, and also the fact that this compound is ferroelectric, as we predicted. So now this is actually a confirmation of the fact that sometimes you may have unusual results coming from a first principles approaches that defy conventional understanding of the chemistry, but maybe we should trust these results or at least give them a chance. And this is exactly what happened in this case. So in a way, this is the third example I'm showing you where using ab initio calculation can really have an impact in materials discovery. So now let me just maybe in 5 minutes tell you a little bit about software. So some of the work that we do is not just based on density functional theory calculations. There is a lot more than that. So, for example, transport requires very advanced, software tools. And for that, we basically use the Quantum Espresso material simulation suite. I just want to flag this up, not because I want to advertise, but just to explain what this is about. So Quantum Espresso is a federation of codes that are based on density functional theory and beyond. So there is a list, for example. And within this consortium, we developed a component which is called EPW, which specializes in everything that has to do with the interaction between electrons and phonons. And Quantum Espresso is probably the second most popular code in terms of DFT calculations for solids, and is the first open source in terms of code, in terms of usage. So just to give you an idea, every year at this point there are maybe about 5,000 people using this kind of software. And as I say, we are responsible for the EPW code inside this package. So EPW actually is something that I started when I was a young postdoc, and this was about 20 years ago, and it was a very tiny code at the time. But now, with the help of many groups, former group members that now are professors around the world, the code has grown to pretty decent size. About 100,000 lines. It's developed by groups in the US and Europe, and now we also have groups in Asia that are contributing. There is a large user community. And many kind of learning resources that we produce over the years. And just to explain, how this works these days, is that at this point, for most of the calculations for advanced materials like optoelectronics, transport electronics, and so on, we don't just use DFT total energies. So the DFT total energy would be basically sitting in this box here. In practice, most calculations today are much more complex. So they involve, for example, total energy, band structures, phonons. Then you need to maybe upgrade your band structure using GW calculations. Then you need to calculate excitons in your system using Bethe-Salpeter approaches. And then you need to patch all this together in order to study functional properties like transport or maybe optical properties. And this requires another two codes like EPW and one-year functions. So all of this actually means that a standard calculation today is not just one single run, but it's really made of many moving parts. So at the very least, for a calculation of this type today, you need to orchestrate 4 different pieces of software. And as you can imagine, that can be a challenge, especially for beginners. And this actually is not just a problem that we are experiencing. This is something that is happening everywhere, simply because calculations are getting more and more complex, and we want to predict properties much more accurately than we could, a few years ago. So to kind of address this challenge, in the group, we've been actually having a parallel strand of development where we are basically putting together abstraction layers, which are, in simple terms, a Python-based software that transfers the complexity from the user, to the machine. And just to give you an example of what I mean, this is a calculation of maybe total energy for silicon. And at this point, with these abstraction layers, in this case called EPWPy, it can be performed in 2 lines of Python. So what this does essentially is to define a material as an object of a class. This material is uniquely identified by the materials project ID, meaning that you don't need to worry about the structure or anything else. The abstraction layer will go and source that for you. We will generate pseudo potentials using existing libraries, and then one just runs a simple calculation by specifying either nothing or some ad hoc parameters that you may need for your specific calculation. And this basically means that today, something that until a few years ago would require preparing large, long input files now can be done, in a couple of lines. And any complex workflow like the ones that we use for carrier transport now can be embedded in maybe 10 or 15 lines of Python. So we believe that this is probably the future of this kind of calculations, where there is really a hardcore, number crunching Fortran base, and then there is a Python abstraction layers that simplify your life. So that's one part of the story. So the second part is that we are collaborating with the Texas Advanced Computing Center in a operation that is sponsored by the National Science Foundation to actually make all of this more widely accessible to anybody. And the idea is that, for example, we would like to remove the challenge of having to install the software, all of the libraries by yourself on your desktop or in your supercomputing cluster. And all of that will have to be delivered on the cloud. So if you go to this website, you will find something called MATSI. So this stands for Material Cyber Infrastructure for Sustained Scientific Innovation. So this is basically a cloud portal that is being developed in collaboration with TAC, where a user can go in, and after you log in, you have access to Jupyter notebooks that are fully integrated with this abstraction layer I just described. And those are something that allows you to perform very advanced calculations without ever installing anything on your laptop. And all of these calculations are executed directly on the supercomputers attack. And the goal for the future is to make this infrastructure available on all of the supercomputers of the National Science Foundation to start with, and hopefully the DOE, in the next step. So the other thing I want to flag up is that we are very invested into training the next generations. So this is just a picture from last year's school on this kind of methods. The reason I'm putting this here is that if you go to this website, you will find a lot of training resources. So if you want to learn about basics of DFT, more advanced calculations, transport, optical properties, and so on, all of that is being recorded, and all of the PDF for the lecture notes and slides is being released on this website. So if you are interested, you can just take a look. And finally, this is just a picture of the group in Austin, some of the sponsors, and on the first line here, and the supercomputing centers that give us resources to do calculations on the second line. And I think with this, I'm at the end of the presentation, and thank you for your attention.
Professor Giustino, thank you very much for an excellent presentation. I'm sure there are a number of questions. I have questions, so we'll open it to the audience. Questions, folks? Well, I'll start with my question, Professor Giustino. So, of course, in the first part where you talked about the post-Moore electronics, the emphasis was, of course, silicon. And of course, from carbon, graphene as a 2D material, carries a lot of promise, and some of us are working in that area. For example, when you showed your fin FET and the ribbon FET, that channel right below it, we could, use essentially graphene. So, what are the works around that in terms of simulation, carrier mobility, and band gap, etc.?
Yeah, that's a great question. So actually, just for background, so you may know that in Europe, there was something called the Graphene Flagship Initiative, which was a $1 billion initiative for research onto graphene.
Yes.
Actually, my group was part of that initiative, and basically we did work on graphene in the area of optoelectronics for a number of years. So the main challenge with actually graphene is being used in some of the 2D materials we know people developing today, but not as the semiconducting channel. The reason being that the graphene does not have a band gap, so it's good as maybe a contact layer, but not as a semiconductor channel. So what people are actually doing now is to sometimes use stacks of when you have a two-dimensional materials like a transition metal like accogenide, then there is an oxide layer, to create, to have the gate. And then on top of that, there is also a graphene layer, or maybe a few layer graphene, or if you want, a nanoscale graphite that is useful in order to screen some of the charges that may be coming from impurities in the channel. So while graphene is not being used directly in the channel, I think it will probably become more and more popular as a outer layer in order to help with the improve the mobility of these devices. In fact, just to maybe make I don't have slides about those experiments, but actually in this group, in this paper last year in Nature Nanotechnology by deans at Columbia, they actually used a maybe thin graphite layer on top of this stack in order to further improve the mobility. So that's an interesting direction moving forward. Yeah.
Okay, excellent. Any other questions, folks?
Thank you for the excellent talk. I'm trying to think about how to relating bottom-up self-assembly of graphene phosphorine heterostructures, either in vertical or lateral fashion. You are talking about some lateral heterostructure. How to relate this to diamond like the carbon structure, for example, doped with phosphor for N-type diamond synthesis. But here I'm trying to see if we can do a bottom-up self-assembly of graphene phosphorine heterostructures. Sounds like very ambitious, but is it doable intellectually using your DFT approach to understand, the connection through all type of bonding topology, hybridization of electronic structures, doping effects. So basically, it could be novel three-dimensional hybrid materials.
Yeah, so that's an interesting direction. So stacking different on the walls materials, I think that could lead to a lot of interesting new science. From the point of view, let's say I can answer maybe from the point of view of calculations and the challenges. So whenever you try to do stacks, you run into the difficulty that you are constrained by the size of your system, meaning that if your layers are commensurate, like lattice matched, that's fine. You can do basically small cells where all these layers are superimposed. If they're not commensurate, things become a little bit more challenging because you need a common supercell that is commensurate with both lattices or with multiple lattices. So then the question becomes what kind of property one wants to predict. So if one is looking, for example, into structural properties, energetics, that's totally doable these days. It's just total energy calculations. If it comes to functional properties, for example, transport or optics, that's more challenges because usually these calculations are 1 or 2 orders of magnitude more expensive than plain DFT essentially. So, for example, just to give you a simple example, if you want to study the interface between these, dichalcogenides with insulating substrate like HBN, that can be challenging because HBN has a smaller lattice parameter, so you will need a supercell which has maybe 4x4 unit cells of those, and then you already run into something of the order of 50 atoms, which for standard DFT is trivial, but for advanced transport calculations is very expensive. So usually what happens is that we discuss with experimentalists and then we tailor the approach to the question, let's say, okay? And the more complex the question, the property you want to calculate, the smaller the system size you can afford. That's a bit the trade-off.
Professor Giustino, one more question as a follow-up. So in your DFT modeling, so you're able to predict new materials. I think the question was also raised with the previous talk. Has there been some correlating work in terms of their synthesis? So what has been your experience? So you're able to predict, but in terms of their synthesis, what kind of dynamics plays in that?
So that's a very interesting and difficult question. So what I can tell you is that maybe 2 or 3 years ago, we were in a panel of the national academies where we are basically asked to look at the DMREF program that I'm sure you're familiar with, and come up with an assessment and what is kind of missing in the current world of maybe modeling. And actually, this is what came up as one of the big kind of knowledge gaps, because as you say, it's one can do total energies once we have the structure, and we can predict new materials. What we cannot predict yet is whether these materials can be synthesized easily or not, or whether you can, you land in something very different. So, I could give you some very positive answer, like a very kind of visionary or optimistic, but the truth is that it's complex. We actually work with the experimental colleagues where we are trying to study a material. They are trying to grow it in large, simple crystal samples, and we cannot go past maybe 200 nanometer, nanocrystals, and that's a problem. And usually we do calculation of phase diagrams, and then we discover there are several competing phases, but that's still a thermodynamic equilibrium. Now, going beyond equilibrium, I think that would require really studies of large phase diagrams, and that's, I don't think, can be done directly with DFT. So I think the two solutions I would see for that is go in the direction of Reactive FF, like was discussed in the previous talk, which is I think already promising and they already demonstrated success in that area. And maybe more recently, with the development of machine learned force fields, I think they open entirely new directions because they are highly customizable. And, there are two trends there. One is to generate foundational kind of force fields that deal with any materials, but most likely any given experiment requires really looking at a few materials. And for that, one can reach very high precision by training specifically on those compounds. And now actually it's pretty easy. It can be done in 2-3 days of supercomputing time. So actually generating new machine learning models that fit really a specific problem is becoming faster and faster. So that will probably address some of these questions. But as it was pointed out again in the previous Q&A question, chemical reactions are not just about total energy. So when electrons moves from one component to another component, that's really a mechanical process. It could be that effect is not that important. So if you make a mistake there, it doesn't compromise the simulation, or that effect could be crucial if it's a rare event on which the reaction depends. And in that case, one will have to do better models. So I think the jury is out there, and we will have to see what happens in that field. But I think things are going very fast. And the pace at which things are moving forward in the simulation and modeling world, it's accelerating, I would say. So probably all these things will become possible soon.
Excellent. Thank you. Question, audience, Carter?
Yeah, I had just kind of a brief question as well about the overarching kind of drivers behind this research and how you start to integrate the machine learning aspect into these features. Do you kind of see this field, since we just talked about the Reacts field and kind of just banking off the question that Dr. Kasang mentioned earlier, do you see this field kind of reaching similar problems that the Reacts has had with kind of the physics being impacted by the machine learning? Or do you kind of imagine, I know that you've talked a little bit about this in your talk, kind of a divergence from that in these simulations being more, I don't know if the right word is akin, maybe, to being able to work with the AI models that are kind of being investigated?
Yeah, that's a great question. And, the honest answer is that I don't know how the future will pan out, but my feeling is that, it's not like one community versus another one. Actually, I think the great thing about, machine learning tools is that they are very widely available and they can be deployed actually, without too much effort. At least at the most basic level. So my guess is that there will be increased integration between all of these tools. Okay, and maybe just to give you some practical example, in my group we're actually starting to embed some of the machine learning model in a high throughput screening of materials. So that's not machine learning force fields, but it's machine learning and neural networks for use for other purposes. Or, for example, to accelerate actual calculations. So all of that, I think it's coming, and I think really maybe something people don't appreciate too much from the outside is that really a lot of this has to do with the fact that there is a gigantic ecosystem of libraries in the world of machine learning and AI, and all of those are widely available. And essentially, as soon as you become compatible with this kind of machinery, you can start deploying them, and that's exactly what we are doing. So apart from the neural network per se or the machine learning algorithm one chooses, it's really being able to interface maybe ab initio software with all of this machinery developed by all these giants in AI. And I think this is happening actually already. We are seeing a lot of applications of that. Most of the focus is on machine learning force fields, I think just out of practical convenience, because total energy and DFT are very widely available. But all of these will be extended to much more complex properties going forward. It's just a matter of time.
Can I ask a quick follow-up to that? Because I think that's very fascinating. As we push towards like more interdisciplinary and kind of interconnected fields, do you kind of see, what are like some of your foreseeable challenges you see, particularly with DFT, kind of trying to integrate these various approaches like you just mentioned?
I think it's more like I don't see fundamental challenges. I think it's just that maybe what I'm I would be cautious about is the risk that since much of this can be done in a black box fashion, new generations may lose may not develop sufficient knowledge of material science, and that's a bit of a concern. So the point is to try and embed these things while keeping the basically domain knowledge intact. I think that's probably a more fundamental challenge for the to maintain the knowledge that we have essentially. Okay, so that's because clearly it's very appealing to run machine learning models. It's very fascinating, and the time to solution, let's say, is shorter than for a fully fledged, let's say, first principles calculation. So it's naturally attractive. But I think understanding the material science that underlies these questions is also very important. That takes time, essentially. So the human learning, in the end, it still has to be done. That's my only philosophical kind of caveat.
Thank you so much. That was really helpful. Appreciate it.
Excellent. It's 12:01, but I take the risk of just one more question, Professor Giustino. So the post-Moore electronics that you talked about. So again, coming back to graphene, you mentioned, I think the greatest problem is, of course, the lack of band gap. So we had some work in what we call 2.5D kind of elements. So probably essentially integrating graphene with some other material so that we get some band gap. Are you? What do you think of these kind of approaches? Familiar with these kind of 2.5D kind of approaches?
So
again, yeah.
I'm not familiar with this one in particular, but I've been looking to band gaps in graphene for quite some time. So at the time there were nano ribbons, or all kind of modifications of graphene that give you a band gap. So the main issue is, I would say, I mean, this is not my answer. Okay, so this is more. Maybe I'm quoting what I hear from companies when we talk to them about devices. The ability to make 2D materials that actually can be scaled up and can deliver performance in an actual device. So let me make an example. If you try to make, so if you need to integrate a 2D material in one of these devices, you cannot just use exfoliation. So exfoliation of graphite with a perfect sample of graphene with extraordinary carrier transport properties. When you grow it by CVD on an 8-inch wafer, it's far from that. So that's the same problem that they have with CVD growth of dichalcogenides, for example. So these are, I think, probably the main challenge. So they are fundamentally all very interesting, but even for 2D materials, getting them to the level of purity that you would match something like silicon that is really produced in exact single crystals with basically barely a single impurity on the entire ingot, that's very challenging, essentially. So going from the lab scale to the device scale, that's basically where there is a very significant bottleneck, actually.
Excellent. Thank you very much, Professor Giustino. Was amazing talk. And today we come to the end of today's talk, and really appreciate your time. I really would like to ask the audience to give a round of applause for our guest today, and wish you a great rest of the day. Thank you very much.
Thank you so much for the invitation.
One more thing, everyone. Since this is a virtual format, we kind of want to get like a group picture. So if you can, turn your cameras on, so then we could have a nice little screenshot.
You could do a group picture, okay?
Yeah.
Yeah, last one.
Like 5 minutes.
Did you get it?
I'm gonna get it now. Okay. 3, 2, 1, smile. There you go. Also, if you didn't sign the RSVP form, please direct message me in the chat so I could just get your email to have it saved.
All right, folks. Thank you very much. Have a great rest of the day.
Thank you. See you tomorrow.
Thank you, Professor Giustino, again.
Thank you very much.